Now we're going to make object tracking more robust by using local features in an image. So let's take a look at how that works. This is an algorithm developed by Goo. So here's the idea. Let's say that here's an image that's given to you. This is your initial image. We are going to find a region of interest. You could apply something like face detection in this case to find this bounding box, or you could manually select the bounding box. That's going to be your region of interest. And we want to track this person over the entire video. So first thing that you do is you apply the SIFT detector to the image. And you get all of these SIFT features. Remember, SIFT feature has location, but also it has the descriptor. So now we take all the SIFT features inside the window and we use that to construct what's called an object model. Those are all the blue points here, the blue features, and that's a bag of features which we'll call the object model. And we take all the features outside of the region, those are the red ones, and we use those to construct a background model. That's again a bag of features right here. So that's your initialization. And now we are ready to do tracking. So here is your new image that shows up, and we want to find this person or this region in the new image. And so what we do first is to apply feature detection to this image. And here are all the SIFT features that we have found. And for each one of these SIFT features, we are going to find the closest match in the object model and in the background model. And if a feature matches a feature in the object model very well, we declare that to be an object feature. And that's colored in blue right here. So you see that those are your object features, the red ones are your background features, and then we also have a few black dots here which are not assigned to either one category because it's possible that you have new features that have appeared in the image that don't belong to either one of these models as yet. So now what we do is we take this window right here and we place it on this image, but we are going to distort this window, that is, change its position and shape so as to grab as many object features as possible. So we want to find the window for which you have a large number of object features inside of it and a small number of background features inside of it. So that becomes the new position of the object. Now remember that the object has changed in appearance a little bit possibly. So we're going to then take the features inside to update the object model and the features outside to update the background model. And then we repeat the process, and that's how we track the object. So this is how it works. We'll start with an initialization process, which is the model building. We're given a frame here, and in this frame, we have one way or the other defined the object of interest, the region of interest. And now we're going to apply SIFT to the image. We get all of these SIFT features. Remember, the SIFT feature also, for each one of them, there's a descriptor that goes with it. Now, all the SIFT features inside the window, we're going to use those to create your object model, bag of features, and then all the SIFT features outside the window, we're going to use those to create your background model, another bag of features. That is your initialization, and now you're ready to do tracking. So here's how tracking works. This is the next frame that's arrived. We're going to once again apply SIFT to this image, and you get a whole bunch of features, each one with a descriptor. So let's say we have K of these features. And now for each feature and corresponding descriptor, we're going to decide whether it belongs to the object model or to the background model. So we find the distance of the feature to the best matching feature in the object model, and that's DO. And then we find the distance between the feature and the closest matching feature in the background model, that's DB. If DB is much smaller than, if DO is much smaller than DB, and in this case we say DO divided by DB is less than 0.5, then we give that feature a confidence that it belongs to the object of +1. If not, we give it a confidence of -1. That is, we believe it does not belong to the object. So every feature now has a C value associated with it. We'll call it the confidence value of either +1 or -1. These are the ones that are shown here which have a +1, the blue dots. The rest of them have a -1 associated with them. Okay, so now we need to figure out where the window has moved, where the region of interest has moved. So that is, we're going to try and identify the new location of the window, W. So for each W that we search through, this is going to be a search process, for each W that we search through, we're going to essentially add up all the C values inside that window, W, and that's what we call psi. That is essentially telling you how much of the object is in that window, or what is the likelihood that that window captures the entire object. And then we're also going to place a penalty for the change in the shape of the window, shape and position of the window in the new frame with respect to the old frame. We'll call that tau. That's just a measure of the deviation of the window geometrically from one frame to the other frame. And then we're going to give that particular window a score that's mu, and that's psi minus tau. And so basically we're going to find the window which gives you a maximum value of mu, MAT score. And that is the new position of the object. And now there's one last step to take care of, which is updating the object model and the background model. So we now have features inside the region of interest, and some of these may indeed be new features, because you see the appearance of the object is changing, and so is the appearance of the background. So we take these features inside the region of interest, the window, WT, and we use the new ones to update the object model. That is, we throw them into the bag of features that corresponds to the object, and we do the same for the background features. We update the background feature model as well. And that's tracking. We go from frame to frame and therefore are able to track the object. So let's see how well this works. So here are two examples, and you'll see here that the method is fairly resilient to changes in scale as well as orientation. On the left here, you'll see that the lighting changes quite a bit. On the right, the person's even spinning around and is being successfully tracked. And perhaps more impressive is the resilience of the method to occlusion or obstruction. So here you see some other objects being brought into the field of view and actually within the window itself. And yet the tracking remains fairly robust, because these features on these new objects have really not been seen before and therefore are not really added to the object model. And so that's where the resiliency comes from. So these examples really show you the advantage of using, instead of using a template-based approach, of using a feature-based approach for object tracking. Now, let's take a look at a few real-world applications. So here is one by Ben Fold. This is just tracking people in the wild. You see that most of the people here are detected and tracked very reliably. There's a rectangle around the person, and in fact, there's a smaller rectangle inside the rectangle which tells you where the head location is. Here is tracking. These are the tracks over space and time. Each one of these tracks corresponds to a single person. And this is a fairly complex scene. There's a lot of obstruction going on here, and you'll see that the tracker works quite well in this case, despite the fact that sometimes there's a very small portion of the person visible. And here is occlusion. So the person goes behind the pillar, but the window is able to somehow track him, and that's because there's a little bit of persistence built into the system. And now, since we are also detecting heads, we can find faces when they are visible, and perhaps apply things like face detection on top of tracking. And here is another application which is a popular one and is actually a simpler one, which is tracking vehicles and monitoring vehicles for moving violations and so on. Since we know where the highway is, the street level is, we know where the camera is, we can estimate the speed of each one of the vehicles. And then there are more recent applications of tracking and motion analysis in general. This is one in the commerce space where you have a shop, and overlaid on a picture of the shop is this sort of heat map. You see that you have temperatures going from red to green. Red corresponds to high values, and that's where people, customers, seem to be spending more time within the field of view of the camera. So this is very useful information because it tells the shop owner, say for instance, where people are spending more time, which products are attracting more attention, and that information can be used for the placement of various kinds of products, but also to figure out which products are worth investing in.